Well, welcome everyone. Today we are going to continue from yesterday's topic. In the last hour of the yesterday's section, we introduced the circuit named flip-flop that allows us to store information for a while until we trigger it to raise it. So that is the fundamental part of a computer, because we need to store information for a certain amount of time. Furthermore, these flip-flops connected with gates, additional gates, are stimulated by a signal that we call clock. Okay, so clock signal changes the state of the flip-flops one after another, just like a moving machine. First step, second step, third step, fourth step, etc. So at each state, multiple flip-flops changes their state, and then the computer works in that way. We also introduced I would like you to turn off your phones if possible, or go into airplane mode if possible, because the access point is overloaded if you are here. So turn off your Wi-Fi's. These numbers are called as hexadecimal numbers, as we have discussed. They start from 0 to F. F corresponds to 16 sticks, 16 beans. The number 16 is the number 16 is something different, because it is 1 and 6. Okay. Actually 16 is 16 is beans. So we call this as 10 in hexadecimal. 10 in terms of numbering system correspond to 16 beans, and 15 corresponds to F. Any questions? If you have any questions, please ask. If you don't, keep silent until you fail. Okay. So with the 4-bit structure, we start from 0, 0, 0 to 1, 1, 1, 1, and then they make up 15 numbers, starting from 16 numbers starting from 0. If you start from 1 to the end, it's 15. If you include 0, there are 16 different numbers here. And as I said, 16 beans is 10, because no beans is 0. Yes. How do we? This is 4-bit. If you think about, you said 16-bit. 16-bit There are 4 of them. Each these are called nibble. Each of them has 4 bits. So total, this is 16-bit number. I like this actually. Okay. So when we talk about numbers, there is some ordering. Now there is delay. For any given binary number, this is an 8-bit number. We have certain regions. We have most significant bit or least significant bits. Most significant bit is at the leftmost part, up here. Least significant bit is on the right. So similar to which part is the most significant? This. Least significant, right. So binary numbers are the same. Most significant, least significant. Sometimes people call it high order or low order. It's a technique to divide 8-bit number into 2. So it means 4 bits and another 4 bits. For 32-bit binary numbers, you have 4 8-bit numbers. Okay. Any questions? So in the computer memory, there is a ladder. Let's wait for the teams. And if you have questions, this. Okay. A computer memory can be thought as a series of buckets, series of boxes, one after another. Each of them has an address, like a post box. First one, second one, third one, fourth one, etc. We call them memory addresses. These are memory addresses. And how do we store information? For example, if I want to store information with this, what can I do? I can, no, as a piece. This means 0, no cap. This means 1 with cap. So with the bunch of pens lying around, I can store binary information. Pens without caps are 0, with caps are 1. So I can save a state. So in ne mi yapıyormuş? I can save a state in several technologies, such as with pen and pencil. I can write zeros and ones somewhere. I can fill glass of water or empty glass of water. So full glass means 1, empty glass means 0. Come in. So I can store information in various means. In the old days, there was a memory type called as core memory. Core memory was something like this. A small, tiny core, just like smaller than a bean. Maybe in the size of rice. It's a ferrite core, magnetic core. You can magnetize it or demagnetize it. If it is magnetized, you can read it with another wire to check which way it is magnetized, or you can reversely magnetize that. So when you read it, you can check the polarity. It is similar to cassette audio tapes. Some of you can remember. So (1950s) and early 1960s, these are the memories that people used. Okay, so these are the small cores, and each of them stores 1 bit. They made arrays with this, and for example, space Apollo 13, Apollo 11, whatever, Apollo program computers used this type of memory in their computers. For example, don't touch that. This is quite a nice picture. Each of them is about the size of rice, or maybe slightly bigger. And they are wired by hand. They are wired by hand with workers, and each row in that, for example, on the right, each row makes 1 byte, 8-bit, 8-bit, 8-bit, 8-bit. So that was those were the hard times. Before that, people used vacuum tubes. There is a way to store information in flip-flop circuits. Okay, like that. So with these flip-flops, as I said, it's like a balancing wood to one side, on the other side. If you tilt it this way, it is considered as 1 or 0. If you tilt it this way, it is considered as 0. So 0, 1, 0, 1. Before invention of magnetic memories, the only way to store information was using flip-flops. Since there was no transistor available at the time, they were done by vacuum tubes, bigger lamps. So they work in the same way with transistors, but they are made of glass, and inside there is an anode, cathode, etc., which is very interesting to work. It was made of vacuum tube instead of transistor. But that was the way of storing information. So today, we can still store information with flip-flops because it is dynamic circuit. with the core memory, no. With the core memory, you can store information as if it is in the memory. But what about in microprocessor? What about in CPU? So those memories are required to be faster. So flip-flops are faster than those core memories or today's CMOS memories, dynamic RAMs. So today we can still use flip-flop type of memories in many places with faster transistors, of course. So just like a magnetic tape, you can read forward and backward through the memory. You cannot read it at once. You need to read it one, take it, another one, take it, another one, take it. So it is like a tape. Okay. In the rektör. Hasan hocam buyurun. Teşekkür ederim. Dersteyim hocam ama müsaitim. Rica ederim hocam. Şimdi mi? İletebilirim. Yani şimdi de iletebilirim, sonra da iletebilirim. Yapay zeka, tabii yapay zeka ile müşteri değerlendirme yaptık. Kurumsal değerlendirme yaptık. Döviz kurlarının forward hesaplamasını yaptık. Yani döviz kurlarında al-sat işlemini yapan algoritmaların dövizin ileriki tarihte ne olacağını hesapladık. Ondan sonra yaptık. Bu müşterilere giderken kullandıkları personelin eğitimi için sesli ajan çalışması yaptık. Ondan sonra daha çok yaptık. Yapay zeka ve veri madenciliği ile kredi değerlendirmesi ve kredi verilecek kişilerin değerlendirilmesi, o konulara baktık hocam. Türkiye Finans. Onlarla hala irtibatımız var. Hatta onlar de hala soruyorlar. Teknopark için bina verelim falan filan şeyleri var. Tekrar canlandırayım ben hocam onu. Oldu hocam. Ben dersten sonra size yaparım. Uzun bir mail atarım. Tamam, görüşmek üzere. Günler. Bay bay hocam. Bay bay. Okay. So, we cannot read the memory as a whole. When I draw, insert, yeni slide. Neyse. Kopyasını kaydet. Okay. Anyway, doesn't matter. O zaman şöyle yapayım. Şurada çizeyim. The idea is we have a memory chip. When we have a memory chip, there is a data port that we call data bus. From these data bus, only one bucket at a time can be read by the computer, by the CPU. When I tell you that there is a circle here, your brain understands that there is a circle. How do you understand? The pixels from your retina maps information to your brain, and your brain matches those patterns with the previously learned patterns, and you conclude that your neural network machine concludes that it's a circle. But if it's a computer, you need to define it, and you need to tell one by one. You need to tell where it is, x and y. You need to say x as a number. You need to say y as a number in Cartesian plane, Cartesian of Descartes, and you need to say radius. So you need to give 3 parameters, one after another. Then the computer realizes, aha, now it is a circle. Cannot take everything at once. So if there is an information in the memory, that should be taken one by one by one by one and then processed. So all the algorithms that you develop requires serial processing of memory. One after another, one after another. Obviously, there are techniques, and powerful processors have multiple units with multiple cores, and there are structures that we call pipeline. Those pipelines can take multiples of these buckets, kind of simultaneously, not simultaneously, but kind of simultaneously. So that makes them very fast. But still, in theory, they are serial, one after another. Yeah. Where are you going to? Good question. Where are you going to put it? If you are not going to put information into cells, where are you going to put? There, where? Okay, good. How are you going to tell which one is X, which one is Y? If you have a place like this, that's a core memory. How many bytes? Oops. Kilitlemem lazım. Okay. Olmadı gerçi de. Ya. Öyle bir şey ilk defa başıma geliyor. Böyle yapsam. Ha. Neyse idare. Ne dediniz? Ha. If you put everything in the same place, how are you going to know which one is which? Which one is which? Because each one has an address. Each one has an address, like door numbers. Door 1, door 2, door 3, door 4. And this memory chip also has address bus input, and address bus input is provided by the CPU. CPU says, get me the one at 7, get me the one at 8, get me the one at 9. So it gives the address to the to the memory chip, and memory chip gives the content of the particular box. If you are going to write something to memory, CPU says, write something to 7, puts address into the address bus, and sends the number so that that number is stored in the location 7. If you don't understand, please ask. I was going to create an empty slide and draw on that slide, but unfortunately the file is read-only now. It will take time to create a copy. If the cell size is 8-bit, 8-bit, only 8-bit. What do you mean by what kind of data? Maybe color or something. Good idea. You have to encode information. For example, you are going to store text. Each letter in the alphabet has a corresponding binary equivalent. We call it ASCII because American Standard for Information Interchange. You have to code it. For example, you are probably familiar with the Morse code. For example, dot, as I remember, dot and dash means letter A. So if one of them is 0 and other one is 1, pick your standard. Americans, since they are earlier than other nations, picked a code standard, which is American Standard for Information Interchange, and ASCII. So they defined it. Everybody uses it. Each letter has a special binary equivalent. So in each cell, for example, this one, no, not from there, from here. Letter A is stored. So equivalent of A as a binary number is stored. Okay. If you don't want to store text, but you want to store color, color can be represented in many ways. For example, if you are not that interested, just like the numbers in Eastern Black Sea region, there are sometimes only few colors. For example, black or white. You can store black as 1, white as 0, or vice versa. So if it is 0, 1 box, because 8-bit, as it can correspond to black, 1, it's white. How about gray? For gray, for example, I'm writing here 0, 0, 0, 0, 1, 1, 1, 1. This is, let's say, gray. Lighter gray, 0, 0, 1, 1, 1, 1, 1, 1. So it depends how you encode information. You have to encode information. That could be sound as well. That could be video. That could be anything. You have to encode, and encoding depends on your standard. Okay. I think good enough. So hard drives. a magnet. There was a magnet video yesterday I posted. Did you watch? So there is a north and south pole of the magnet. If you put a neutralized iron near a magnet, what happens? This becomes polarized. Okay? Normally, they look very different places, but if the magnet comes nearby another iron, the atomic polarities align to the same direction. Do you understand? If you do the other way around, these polarities are reversed. So because each iron atom will try to act like a magnet, they become magnets. So by having a disk rotating, actually in the old days, IBM Tron. This is okay. I don't need to show the. So in the older days, there wasn't disks. There was. It comes. In the site. Okay. The magnetic material was covered on the drum. The drum was rotating. Okay? And there is a magnet, electromagnets. What's an electromagnet at each location? Electromagnet means magnets, but electrically controlled. So there is no actually magnet. There is a wire, an iron. If you give current, it becomes magnetized. If you give the current in other direction, north and south changes. So these are magnets. There is a read and write heads. One of them is read, one of them is to pick up. If you get close to a wait, I have an ability here. This one. Okay. So which one? This one. If you have a current and some iron here, a magnet effect is present around. So magnetizing effect is produced with the current. If the current flows in the other direction, effect is reversed. So this is for writing. For reading, like this. Oops, sorry. If you get closer to the reading head, and move your magnet, current starts to flowing. If you move this direction, current starts this way. If you pull back, current starts other direction. If this is south and north, which was programmed with the writing head, current flows in the other direction. So by checking the polarity of north and south, it is possible to pick up polarity from a certain iron piece. Is that clear? You can magnetize it, that location, regionally, and pick up the existing condition. Is that clear? So those guys invented something like this. What they did was, how am I going to add another page? Swap the page. Go back. Close it. Add. No. Okay. Okay. What they do is they make a drum. They divide the surface of the drum into tracks. Each track is divided logically as squares or rectangles. And each one can be magnetized and demagnetized north-south or south-north way by writing head. Okay, and then can be picked up by reading head. It has two wires. If the current flows in this direction, it is 0. If the current flows in this direction, it is 1. Is that clear? So they made multiple heads so that they can store information as the drum rotates. This was not a hard drive. This was actually RAM those years, because there was no RAM available. So all the information stored for further processing with the flip-flops made by vacuum tubes were stored in these drums. And actually, old computers were not named as computers. They were named as drum machines at the beginning, instead of computer or some other machine. People called it as drum machine. Oh, my battery is gone. Okay. So these are the drum machines. I am going to show you. Okay, this. Listen the sound. Wait, read. Okay. There was another memory, but doesn't matter. It's going to start from the beginning. No? So this is a hard drive. It rotates. Now you can understand everything. Instead of having multiple read and write heads, they decided to move the head. So it became a hard drive head. Today we have flash drives, flash-based drives, solid-state drives, SSD. Solid-state drives does not have moving heads because the capacity, our capacity and cost limitations to store information in transistors is reduced so much so that we can fabricate it in a small density, in a small size, and sell it. But still, even today, hard drives are a little bit cheaper in terms of cost per gigabyte. It's also stable, yes. It is up to you, not necessarily. No, when you have a magnet, I understand. When you have a magnet, when the electricities go out, does it forget its polarity? So what is your question? It does not forget its polarity because it's magnetic. However, if you wait long, very long years, the magnetic field of the Earth slowly changes the content of the hard drive. So there is that kind of effect. It is also visible and audible in audio tapes. Very old audio recordings have slightly degradation due to global magnetic field, but not that. Yeah, hard drives. These are the tapes that you see in old movies, in computer rooms. They were tapes. So reading and writing was done. Reading and writing was done in the head part, just like a cassette player. So zeros and ones are recorded. Each location is called a sector. These are called a sector. And this is called as track. Your hard drive may have more than one plate. This is called platter. This is track. And this one, track sometimes called as cylinder in some places. And it rotates. The problem is to move the head in and out quickly so that it can access to all the tracks one after another. That is important. It's not connected like your brain. Your brain has connections from multiple places to multiple places, so it works like a neural network. You are going to learn it later. But computers are more sequential. One after another, but very fast. So your question, the word hello in a coded form in the memory. H has a corresponding code like this. E has a code. These have corresponding codes, and then when you store that in the memory, it becomes hello. For the computer, hello has no meaning unless you are doing natural language processing program. Even then, natural language program does not understand hello. It is understood by the program. So hello has no positive meaning for the computer. So unless you associated it with the number, positiveness number somewhere else. So everything depends on you. Everything depends on how you interpret, how you encode things. It doesn't go by itself. That's clear. You are going to code it. You are going to enumerate it. You know what enumeration is? Enumeration means if I say this is 1, this is 0, now I enumerated 2 cases. I am defining it. So difference between base 10 and base 2 systems as a recap. With the base 10 system, 375 is one from 0 to 10. It's the first digit. From 10 to 100, it's the second digit. From 100 to 999, it is the third digit, of course. For the base 2 system, there is 1, 2, 4, 8. So 2 to the, this part is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So these are the digits. I think that's clear enough. If it is not, please ask. Ask a question. 2 to the 3 means 2 times 2 times 2. Huh? I can't hear. This one can show numbers up to 2 to the 0. 2 to the 0 is 1. So it can either show 0 or 1. This one, 2 to the 1. It is either showing 2, the presence of 2, or non-presence of 2. Yeah, for example, there is either 8 or nothing. There is either 4 or nothing. There is either 2 or nothing. There is either 1 or nothing. So if there is, we say there is 1. If there is no, 0. So for example, 1001 means it's coming. It is incredibly good, right? I liked it. So when you have 1001, last one didn't come. When you have 1001, that means 8 plus 1, which is 9. Because there is 8, there is 1. So that's why I said 2 to the 0, 2 to the 2, 2 to the 2 to the 1, 2 to the 2, 2 to the 3. Any questions? Evdeki arkadaşlar nasıl vaziyet? Şey yazmışlar ama. Geliyor demiş. Evet. Şey daha yazdılar. Bakıyoruz yazdıklarınıza. Yazdığınıza bakmam biraz daha şey oluyor mu? Gayet iyi hocam. Tamam. Okey. Sesli de cevap verebilirsiniz arkadaşlar. Çünkü elimde değil. More extended version of the same problem. When you have 101, 101 as a binary pattern, which is consisting of 6 bits, there is 1, there is 0, 4, 0, 0, 32, and the total is 37. Here's 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. 2 to the 5 is 32. 8. They made a mistake, actually. This must be 1. Did you see that? So there is 4 and there is 1. 45. Okay, let's move. An algorithm to find the positive representation of a positive integer. How am I going to find a number equivalent of binary equivalent of a decimal number. For example, let's say 9. Divide 9 by 2. Let me do this way. 9, 2, 4, 8, 1, 2, 2, 4, 0, 2, 1, 2, 0. So what you take is 1, 0, 0, 1. That clear? No. No, that's correct. This is how you divide. So you start dividing, the remainders are written as digits. This is not frequently required, but since we are going to measure whether you study or not, these kind of questions can come up in the exam as small questions. This is the American style of division that we don't teach in Turkey. So instead of doing this, they do this. But the same thing. Any questions? Verelim. Let's give a break. Let's give a break for 10 minutes. Evet, arkadaşlar konuşabilirsiniz, dinliyorum.
Hocam bazı harfler.
Hocam.
Dinliyorum. Sesin iyi geliyor. Ömer, go ahead.
Teacher, I'm wondering if you can post the upload the slide on the Teams, because we barely can see the slides you're putting on the screen. It's like far away and scrubby.
I am sharing the slide. Don't look at the screen from the video. The slide is also shared.
Where should I go? What's it called?
I don't know. Probably you zoomed into my image. Don't zoom into my image. Select the slide view.
Slide view.
We can select, teacher. It becomes dark when I select it. We can select slide. There is a mistake in the program.
I can see the slides clearly.
We can see it on the right top of the screen, but we can click on it.
Diğer arkadaşlar görebiliyor mu? Çünkü ben de bağlıyım. Ben görüyorum.
Ben görebiliyorum.
Benim
şeyi.
sınıfta
Ben de
gösterdiğim
görebiliyorum.
aslında sizin gibi bağlıyım.
Bazen öyle siyah oluyor ama bekleyince düzeliyor.
Ha, gecikme oluyor. Yani şu anda mesela benim başımda bekleyen insanlar var. Oradan takip etmeyin dersi. O sınıfın havasını alın diye koydum onu. Evet.
Şimdi bir bilgisayar var demiştiniz eski şu an modelini
Aa.
hatırlamıyorum. Onu
Bak.
bir gün görme imkanı var.
Odaya geldiğinde görürsün.
Şey, merak etmeyin. Benim de soru soruyorum. Sağ olun.
Hocam hard disklerin kapağını açtığımızda bazıları ölüyor. Neden ölüyor? Yani
Genelde parçalar oynuyor. Kafa metale sürttüğü zaman bozuluyor.
yani ışıkla falan alakası yok.
Hocam az önce siz dediniz yani biz buradaki dataya erişmek için bunların hepsini okumamız lazım.
Hayır.
Step by step'ten.
Şöyle bunda trackler var. Bu var, bu var, bu var, bu var, bu var, bu var, bu var, bu var, bu var, bu var, bu var, bu var. Ondan sonra bir sonraki var. Ondan sonra bir sonraki var. Yani bunu okumak için kafayı buraya girek götürebiliyorsun ama ondan bir tane okuyorsun. Bir sonrakinde hello diyelim. Önce hey'i okuyorsun. Sonra l'yi okuyorsun. Sonra bir daha l okuyorsun. Bir daha okuyorsun. Yani hello'yu lök diye almıyorsun.
Alamıyorum. Yani eksi sakınım olsa bile geçemiyorum.
Yok.
Alamıyorum diye.
Hayır şöyle. Ben hey'i alacağım. Sonra da o'yu alacağım diyebilirsin.
Mesela
ama
benim
hello olduğunu anlayamazsın.
Sadece h'ye eksi tokenim var. O'ya yok.
Sadece hey'i istiyorsan gidip hey'i okuyabilirsin.
Ama ondan önceki bilgileri okuyamıyorum.
Okursun. Nerede olduğunu bilmen lazım.
Nerede olduğunu bilmem lazım yani. Eriştiğim zaman
Normalde şöyle okuyorsun.
RAM yapısını bilmem lazım.
Başkası paylaşmaya mı başladı? Niye? Birisi ekran mı paylaştı? Oldu.
Mesela hocam ben bir sunucuya eriştiğim zaman sunucu bana sadece bir istek dolduruyor. Ben de isteğimi RAM üzerine belirttiğim zaman sadece bir yani decimal geliyor. 8 bit geliyor. O 8 bit de hexa'ya döktüğüm zaman mesela A, B. Yani bunun için daha önce gelen
Sunucu
bilgi
falan değil mi? Öyle deme. Bilgisayarda.
bilgisayar. Mesela bunları daha önceden de alamaz mıyım? Yani gelmiyor. Erişim.
Ben Teams'e gidemiyorum. Duyurulardaki linke girerim, bir üye yazıyor. Ama nasıl girebilirim?
Bana mail at.
Direkt mail atayım.
Mail at. Ben sana gönder yapayım.
Tamam.
Mail irtibat. Böyle iyi oldu değil mi? Tablet çok hoşuma gitti. Bir de tabletin mikrofonu aktif. Diğer arkadaşlar mikrofonundan alıyorlar yani. Elimdeki mikrofondan alıyorlar. Burada sadece şeye bağlıyız işte. Network iyiyse bu güzel çalışacak. Network kötüyse sıkıntı, onu da çözeceğiz inşallah. YouTube'a da koyuyorum. Nereden? Ha? Attım ya, kanalın en başında atmıştım. Burada var diye. Benim kendi sayfam. YouTube'a Mehmet Göktürk yaz, çıkıyor. Şapkalı bir resmi var. Dün gece koydum. Canlı yayın alet nereye, bir yere gönderdi ama nereye gönderdi bilmiyorum, hangi hesabı. O da o kadar iyi değil. Neden dersen o tahtadan gösteriyor. Burada direkt ekrana paylaştığım için böyle daha iyi. Rektörün konuşması da çıktı.
Şimdi bize de her türlü para istiyor ama. Çalışmak için veya öğrenci için gidince yurt dışı vizede.
Vize hangi ülke?
Mesela Avrupa'da.
Vize parası vereceksin tabii. Vize parası vermeyeceksen nasıl gideceksin?
Bize parası değil. Mesela şey istiyor ya, bankada şu kadar miktar dursun diye Avrupa.
Hayır, iş bulduğunda onlar kağıt gönderiyor zaten.
Yüksek lisans için gidince.
Orada sorun yok.
Ama lisansta ben
Turistik
öyle görmüştüm, o
giderken,
yüzden yani.
turistik giderken, hatta turistik giderken bile tipin düzgünse gene bir sıkıntı yok.
Lisansta?
Gene yok.
Lisans için gidiyor mu?
Ben Amerika'ya gitmiştim lisansta, turistik. Süresiz vize vermişlerdi. Ki sonra o kaldırıldı, yani ölünceye kadar.
Öğrenci için gidince peki.
Gelirse gelsin diyor ya, iyi diyor zaten.
Allah Allah.
Yani orada gidip de işçilik yapmanı istemiyordum.
Hocam ben bayağı doldurmuştum bize başvurumu. Sakallı olarak koydum. Bana
Fark ederdim.
Tıraş olup mu?
Ha, şimdi değişti tabii. Ben ta 1986'da, 87'de.
Bak,
Evet.
Bir şey soracaktım. Benim 107 dersimle 233 dersim çakışıyor. Nasıl azalıyor? Nasıl yapabilirim?
Bilmiyorum nasıl yaparsın işte. Dediğim gibi yap. Daha önce bu ders aldın mı?
İki sene almıştım.
VF ile mi kaldın?
Tefe yok ne hala.
Ne ile kaldın? Devam mecburun var. Online
İşte
veya
o- İkisi de laboratuvar dersi.
bir şekilde
İkiye bölmüşsün galiba 107 dersi.
neyi?
107 dersi.
Yüzde evet. Böyle. Onu asistanlarla konuş istersen.
Tamamdır.
Hocam şimdi bu dönemde ben kaldım da geçen 101 ile 102 aynı anda alırsam bir dönem object açılıyor mu?
Bilmiyorum. Gerçekten bilmiyorum. 101 ile 102 aynı anda alınabiliyor mu?
Almıyor ama işte object'i veremiyorsan bir anlamda. Alabiliyorsun.
Daha önce nasıl kaldığına bağlı belki.
Ya ben alabiliyordum. Ders teksi çıktı yani. Yusuf Hoca'ya da sordum. Danışman hocam oydu. Alabiliriz mi dedi.
Daha önce aldıysan şöyle olabilir. Daha önce aldıysan alabilirsin. Almayabilir, çıkmıyor. Sen kaçıncı sınıf? Bundan da kaldın. Neyle kaldın?
Bir şey mi diyorsun? C++ mı
Çakışmıyorsa alınabilir yani. Ben değiştim, hidayete erdim diyorsundur.
Alırsak lazım yani.
Alınabilir yani. Evdekiler kamerasını açmadı bak. Güzel güzel resimler var ama. Evet arkadaşlar, başlayacağız.
Hocam okullar kapalı mı?
Ha?
Okullar kapalı mı? Geri kapatırlar mı?
Bu kadar yakın oturursanız kapatırlar. Maske yok, bir şey yok. Bende de yok. Benim pencereyi diğer dersleriniz nasıl? Matematik? Online mı? Fizik de online. Bu da online. Tamamen mi online yapıyorlar? Yani ben online şeye zorluyorum. Şansımı zorluyorum en iyi şekilde. Dolayısıyla hani bu şekilde size uygunsa online'da olabilir. Yani ben gene burada olacağım da online olabilir yani. Olsa iyi olur. Çünkü kapıda 50 yazıyor biliyorsunuz. Şimdi 3 bitlik sayılar var. 4 bitlikler var. 7 var. 8 var. 12 var. 16 var. 24 var. 23 var bazı eski makinelerde. 32 var. 50 var. 64 var. Bit sayısı. bigger is the better. Probably because of everything is
Hocam ders devam ediyor mu? Diyor mu? Biz duyamıyoruz da şu an.
şimdi beni duyuyor musunuz?
Aynen şimdi geldi.
Geldi de görüntü gelmiyor değil mi?
Yok.
Ha geldi. So how am I going to represent minus numbers, negative numbers in binary? The idea is I have 1001 as 9, right? So this is minus 9. The answer is no. It is not minus 9 because in the computer memory that I was talking about, the buckets locations, there is no place to put this sign. It's not available. So what am I going to do? I am going to do this way. Don't look at the other parts. This is 1, 0, 0, 1. I am going to use 5 bits instead of 4. If there is 1, it means minus. If there is 0, it means positive. So when you have, of course, the architecture of the computer is of, for example, 8-bit, if you have 8-bit memory, and if you want to store negative and positive numbers, right? Eight-bit. So the leftmost bit is reserved as time bit. If there is 1, it is negative. If there is 0, it's positive. The rest is interesting. But there is some slight difference. The problem lies around I'm going to use the free space here. The problem lies around when you have number line, sayı doğrusu, line of numbers. You have 0, you have 1, you have 2, you have 3, -1, -2, and these goes to infinity, right? However, if you keep adding to a binary number, what is the maximum number you can achieve with this? Think about all positive. 255, right? What happens if you add one more? For example, 1, 1, 1, 1, 1, 1, 1, 1. In the old cars in the open car shops never exceeds 100,000 kilometers. The car is very old, but still under 100,000 kilometers. Why? Because number of digits is 6. So if you pass 100,000 kilometers, how many times God knows, but your car still looks new on the paper. So similarly, if you exceed number of digits available to you, this becomes 0, 0, 0, 0. If you increase once more, 1 kilometer more, everything goes back to 0, 0, 0. Do you understand? So in binary numbers, instead of number line, right, we have number circle. So the number circle. 0 here, 255 here, 255 plus 1 brings you back to 0. So the idea is, when you are talking about positive and negative numbers, if it is the line, this is the negative number, these are the positive numbers. Beni duyamıyorum mu diyorsunuz? Duyuyorsunuz ya, mikrofonum açık. Siz konuşunca ben duyuyorum. O şekilde bir sıkıntı olursa tamam, problem yok. Okey. Bakayım. Ekran büyüsün. So we have negative numbers and positive numbers here. Hasta olmasın değil mi? With the number circle, we have positive numbers and negative numbers. So from here to there, all numbers have 1 in the most significant bit and something, something, something, something, something, something, something, and something. Up here, you have 0 and something, something, something, something, something, something, something, something on the right side. It's interesting. So where is -1? -1 is here, right? So logically, if 0 is here, 1 is here, -1 should be here. Do you understand? Now listen carefully. What is 1? This is 1, right? What is this? No. Ters köşe. No, because this is here at the bottom. So the people invented a notation called 2's complement. 2's complement notation says it's here, so -1 is actually 1, 1, 1, 1, 1, 1, 1, 1. Huh? Last one is add 1. Let's see. No, it's 1. The idea is invert everything and add 1 in order to find negative of a number. For example, in order to find negative of 0, 0, 0, 0, 0, 0, 0, 1, invert everything 1, 1, 1, 1, 1, 1, 1, 0, and add 1. The net result will be 1, 1, 1, 1, 1, 1, 1, 1. And obviously, it is 255. Just before 0. And there is also an interesting thing about numbers. When you talk about real numbers.
Teacher, can I ask something?
Yes.
We are adding 1 because of the 0?
No, that is the rule.
Rule, okay.
And I am going to explain why at this moment.
Okay, I'm waiting.
in the number line, these numbers represent certain places. But in computer, that's different. Because there are no fractional numbers. There is a way to represent fractional numbers, but in computer memory, it's again binary. So you cannot have 1, 0, 0, and little bit 1, meaning half. So it's not possible. Right? So instead of occupying certain locations in number line, when you are moving to digital, this is very important for the rest of your life, and it gives you some understanding, because it is also the reason of certain errors. Some bad students think that the numbers in computers are real numbers, or numbers like in mathematics. Actually, they are not. There is a limit. Cannot have half and half one. It is either 0 or 1. So when you are talking about 0, 0 does not represent here. 0 represents here. 0 represents a region. Okay? Anything there is 0. Anything here is 1. So when you talk about circle, 0 is here. That's clear. 127 is here. And 127 is hexadecimal 7F. 7F means 0, 1, 1, 1, 1, 1, 1, 1. Okay? The biggest positive number in 8-bit. But it is still on this side. The next one is 80, 80, which is 128. You understand? And then you have 255 here. So because 0 is not at the center, but little bit on the right, we add 1 in order to find a negative version of a positive number. There is one offset all the time. It is not ideologically shared like real numbers. 0 corresponds to the entities between 0 and 1. So everybody shows the right side. Therefore, if you want to go to the other side, you need to pull back 1 by 1. So two's complement notation system actually requires adding 1 after inversion, or subtracting if you are coming from the other side. So with the 4 bits, you have minus numbers and plus numbers. How many positive numbers you have here?
8.
8, yes, 8, because there is 0. That is the reason that we are adding 1. How many negative numbers? Again 8, but since it starts from -1, because there is no -0, okay, it goes back to -8. And similarly, if it is 8-bit, it goes from 0 to 127, -1 to -128. Is that clear?
Yes. Yes. No.
Okay. Ask a question. Who said no?
I didn't understand the adding one station.
Okay, I'm back. Network is gone. So since 0 is here, nerede bu mu gitti? Geldi. Allah Allah. Şöyle yapalım. Şöyle yapalım. It's connected. Back. So since we have 0 here, we need to add 1 because we don't have -1. You can think of that way. We don't have -0. We only have -1. So in order to balance -1 with -0, which doesn't exist, you add 1. I explained this. I explained this. Yes.
How we know
If we
1 like that? How we know?
Good question. How do we know?
Can you repeat?
Let me repeat the question. If we have 1, 1, your friends ask, do we know that it is 3 or minus 1, yes. Which one? Go ahead. So here we have 0, 0, 0, 1. It's okay, I think it's going to come. Bad mad ama. Ha gayret. Namuzafferiyet. Ha, geldi. So 0, 0, 0, 1, 1, 0, 1, 1. So it is either this is minus 1, right? In terms of regular numbers that we know. This is positive 1, this is 2. No, this is 0, this is 1. This is minus 1. No, this is not minus 1. Yeah, this is minus 2. That's minus 2. 0, 1, minus 1, minus 2. So, but how do we know that we meant 3 or minus 1? It could be 3. 1, 1 is 3. 2 to the 0, 2 to the 1.
It isn't saying things.
Söyle. You can talk in Turkish. If you want.
İkili sayı değil.
He said it is not two's complement notation. But how do you know that? It is only assumption. No. It's only assumption. And furthermore, microprocessors doesn't know about it. You know as a programmer, you know as an architect, program architect, you treat them as signed numbers or unsigned numbers. And the name for it is actually, we don't use two's complement, we have signed numbers or unsigned numbers. Actually, those of you or some of you are familiar with C, you have int I, right? And there is also unsigned I. So it is defined in the program and you treat it as signed number or unsigned number. Nobody else knows. And that is one of the reasons of failures in applications and crashes in the programs. Some programmer believes that it is a signed number. Some other part believes that it's an unsigned number. So when you share data, if the number is small, no problem. But if the number is big, it goes to the other side of the circle. When it goes to the other side of the circle, it is treated as a negative value. There is a famous accident for that, a French accident. Ariane 5 rocket failed, and they had over 1 billion euros lost in the disaster. And the reason is this, because the older version of the software used for the bottom part, the engine part, was for the previous generation of rocket, Ariane 4. They used the same rocket, but the upper part was the newest part. So one part was thinking that it is the number is more than 32 bits. The other part was thinking that the number is smaller than 32 bit. When the rocket engine acceleration exceeded 32 bit number, it is interpreted as a negative number on the other side. It was positive, it was increasing positive, but the other side treated as a negative number, then it's failed. Let me show. Oops. Ariane 5 accident. Okay, this is important. That's the video. Herkes böyle mutlu falan. ...32 bite yaklaşıyor. 1-1-1-1-1 oldu şimdi hepsi. Bitti. Eksi tarafa geçti. ...37 seconds. Suratlara bak şimdi. Aşağıdakilerin. Evet arkadaşlar, diğer şeyi bağlarken sesi buradan duyabilirsiniz. Bağlamada. Tableti tekrar bağlıyorum. So, this signed arithmetic, signed integers and unsigned integers, okay? Limitation of number, for example, after 255, there is no number. 255 plus 1 is 0. So your design should use the numbers that are smaller than 255. If there is a possibility, in that case, if there is a possibility, then you should not use 8-bit numbers, you should use 16-bit numbers. If 16-bit is not a number, then you should use 32-bit numbers, 64-bit numbers, whatever is necessary. Because it's just like automobile kilometer count, it rolls back to 0. I think, let me join again. Atıyor ya.
Hocam mikrofonunuz kapalı, duyamıyoruz sizi.
Sorry, now how I'm going to store information in the computer memory. For example, you have a sound wave or you have an image, a real world signal. In certain places, you measure it, and after you measure it, you convert each entity into numbers. So measuring is set to be named as sampling, and converting that sample to a quantity that is in binary conversion is said to be quantization. So sampling and quantization is done, for example, when you are making a studio record of certain singers into digital. You sample, then quantize. You say 7 volts, 7.1222 volts, and you say that is 101101. Some part is lost because the next number is this. Next number is this one. So there is no other number in between. So this quantization is actually either here or here. Nothing in between. So digitization actually loses certain part of the information. Very tiny details are lost because you are either here or there. Understand? So that's called quantization, and there are effects named as quantization errors. Staircase appearance in the images and the low quality images have quantization errors because the conversion results in low bit samplings, low bit information, and most of the information is lost. You can it should be stored in analog. That's analog. So the old record players are analog. Also, cassette tapes are analog. So cassette tapes, there is no quantization, there is no digitization. But in CD players, there is a quantization. So 16-bit, each waveform is converted into 16-bit numbers at each location. And how frequently sampled? 44 kilohertz. Means 44,000 times per second. Number is measured from the sound wave and stored in computer memory. So that becomes CD quality sound. How is? Good question. There is a device called analog to digital converter. AD converter. AD converter has an analog input, digital output. So there is a sample and hold flag as well. So microphone is connected here, microphone amplifier, whatever, headphone jack. So analog to digital converter gives numbers. Whenever you give pulse from here, so you give 44,000 pulses per second from here, and it gives out 44,000 measurements per second for the sound. For GSM, for example, I think it is 8,000 for telephone conversation, because quality is not necessarily required to be good, because high quality means more data. More data means more money for the Vodafone or Türk Telekom, etc. So I said there is no 1.5. 1.5 does not exist, I said. But if I want to, what am I going to do? I am going to do this way. I am going to use exponential notation. For example, what I am going to do is 1527.25. There is numbers here. It's not binary. So the standard way of thinking is 0.152725 and 10 to the what? Yes, I think. What am I going to write here? Tell me. 4. Hala bir çekingenlik var. Is that clear? Is it plus or minus as I wish? So there is some information here, some information here, and some information here. Is that clear? So, but this is decimal. Can this be binary? Yes, like something like this. I don't care. The problem is this is 10 2 to the 0, right? This is 1/2, 1/4, 1/8, and so on. So if you go from decimal point to the right, it is 1/2 to the 1, 1/2 to the 2, and so on. To the right, half, quarter, etc. Yeah. I am going to tell you. Because in binary, there is no 7 here. 7 is another binary number. You should make the division, store the result. So the idea is, this is called as antissa. This is called an exponent. This is called a sign. So the people, the scientists, computer scientists, agreed on, it's all agreement. If I don't want it, I can select. But they agreed that, for example, I can store the sign bit on the right side if I want, but I didn't. So there is a sign bit, there is an exponent, and there is a mantissa. So this way, I can store fractional numbers. And we say that it's a floating point number. Okay. And for the 32-bit, floating point numbers are usually, unless you are programming small microprocessors and controllers, usually 32-bit in the PC world. When you say float in the C programming language, it is 32-bit. Or when you say long, or when you say double, it is 128. Or 64, it depends. There is one sign bit, 24-bit for the mantissa, 7-bit for the exponent. Okay, so that kind of number, those kind of numbers can be represented. But the biggest problem is, biggest important thing is, this part corresponds to number between 0 and 1. Do you know the problem of 1 over 2 plus 1 over 4 plus 1 over 8 plus? Yes. From the exam? So it can never reach to 1. So the right side is made up of those numbers, either 1 or 0, 1 or 0, 1 or 0, 24 bit. So the smallest one is what? 1 over 2 to the 24, which is very small number. So that kind of precision can be achieved. That's what floating point is. Hala buradan değiştirmeye çalışıyorum. So your question, 2 times 5 over 8. 5 over 8 is 101. 5 over 8 is 101. 2 is here. So 101 comes here. But since mantissa is okay, I'm going to finish the class. It's about time. So wait. The idea is you write 1010 to the mantissa, and to the exponent you write 2. You write 2 here. You write 2 here. And 0 here. Thank you for coming today.